welcome to NPTEL course on power system protection. On distance link, in today's lecture, we will go to application on double circuit line. Our focus will be on protection aspects on double circuit line, and then we will see how distance delay can be applied for such a transmission system protection. Now, before going to that, let us be clear on two terms, the underreach and overreach of a relay. So, what we see, let us consider this transmission system and we have a relay at the bus M. So, consider distance delay in zone fault at F. So, it is inside the zone 1. Now, if the relay now finds the apparent impedance to be greater than the actual fault impedance, positive sequence fault impedance, then we can say that the situation is underreach. Once again, a distance delay is said to be underreach when the impedance seen by it, that is the apparent impedance, is greater than the actual impedance to the fault. The percentage of underreach is calculated in terms of the Z setting, like 80% of the positive sequence impedance of the line, also minus the Z apparent divided by the Z set into 100%. So, this you can say that when we say this, we mean that at the reach of the relay, what the corresponding apparent impedance seen by that. So, if we use this one, then we can see that what is the percentage of underreach. Here what we like to see is that underreach implies that the relay will see, because of the apparent impedance being higher values for the fault point. So, it will not reach up to the zone 1 setting of this point. So, before that it will be observing the required impedance setting. In case of overreach, when the impedance seen by it is less than the actual impedance. So, whatever the actual impedance, if it sees the lesser value, then the corresponding situation is called overreach situation. So, in that case this relay will see even the zone 1 beyond this also. So, again the corresponding relation for overreach will be similar to that. Now, we will go with the in this lecture on double circuit line protection, application of distance delay. Many lines in transmission level are being of double circuit in nature. We have discussed something in the directional relaying application also. Now, if you see the structure here in this tower, then we see the left hand side we have 3 bunch of conductors, but they are each bundle conductors, and in the right hand side also we will see, you can say that a set of 3 conductors. So, if you remember in the inductance calculation, capacitance calculation, we use set of conductors, multi conductor system A dash, B dash and C dash. Suppose this becomes A of one circuit, this becomes A dash of another circuit, B dash and C dash. So, this kind of transmission system having 2 circuits we consider in terms of that, and that you can say that not only gives us more power to be sent and also other advantages in terms of inductance reduction and so. Now, in such a case we see that on the same tower both circuit 1 and circuit 2 are available, and that is you can say that the issue which arises and it needs special attention on protection perspective. We will see. Now, let us will consider a simple double circuit system. However, double circuit or otherwise called also parallel lines can run on same tower, can be running on different towers on the same nearby right of way. They can be terminated at different nodes. They can be have a common bus also, and the other bus may not be common. So, there can be different configurations on double circuit line in a power system. We will consider a simple such a structure where we have the two buses M and N, and in between them we have two parallel lines or two circuits, like the tower I showed you, where we have two circuits on the same tower. Now, let us say fault happens to be there at F, which is internal fault in circuit 1. Now, what is the issue with overcurrent and directional linear approach? We will first see, and then we will proceed for the requirement of distance relay protection. So, when a fault happens to be there, we see this is a radial system. So, fault current will flow from this path, and also fault current will flow from this path. So, in the directional laying lecture, we mentioned that we essentially require a directional relay here in addition to overcurrent relay, and here for this breaker also, fourth breaker also we require additional directional relay with overcurrent relay. We have overcurrent relay this side and for both the circuit breakers. So, the objective is that for an internal fault in any of the line, that line should be only out, the other line still should be functional. This is from the selectivity point of view. So, for that, in this case what will happen, whenever a fault happens to be there this side, this directional relay sees forward direction DR1, and then the OC3 also will see large amount of current. So, therefore, this combination will open the breaker at 3. Now, therefore, the fault current path from this route now is no more there. So, this OC2 at breaker 2 and OC4 at breaker 4, they will not see no more fault current. So, therefore, this circuit will remain intact because they will not operate the corresponding breakers. Now, from this side at breaker 1, this fault is still, you can say that continuing. So, this overcurrent 1 here will see the large current, and there is a coordination between OC1 and OC3 and OC2 and OC4 respectively. So, therefore, in a delayed time OC1 will operate after the clearance from the circuit breaker 3 side. So, this is what the parallel line is being protected by overcurrent and directional link combination. But what we see from here that the breaker which is closer to the source side, substation side otherwise, is having, you can say that, a delayed operation. So, which is not a good thing from protection point of view. So, therefore, that is one perspective of the demerits of such a protection philosophy. The second thing is that if the corresponding fault happens to be resistive fault, higher and higher resistive fault, then the current amount decreases, and therefore, the overcurrent relay may find limitations in terms of that, or it may be a delayed operation and so further delayed operation and so. So, with such limitations of overcurrent principles here, there is a alternative, and the alternative we are talking about here today is on distance link application. How the distance relay can be applied to double circuit line more efficiently, that we like to see, but before going to that there are issues. So, let us see that issue. We have circuit 1, circuit 2 or line 1, line 2, fault happens to be there in one of the line. Then we have already analyzed that these circuits, fault analysis can be for this circuit can be analyzed in terms of positive sequence, negative sequence and zero sequence component and associated impedances. Now, let us consider only the current part. So, when you say positive sequence current, or negative sequence current, they are balanced. So, therefore, in that faulted phase, the positive sequence current and the negative sequence current, they being balanced, the associated current I A 1 plus I B 1 plus I C 1, all the 3 phasors summation will be 0. So, therefore, the corresponding flux which will be out of these 3 lines encircling that one, if you remember the inductance calculation. So, that becomes 0 because that circle encircles summation of these 3 currents which happens to be 0 for positive sequence current. So, therefore, the flux linkage to the from one circuit to the other one, that becomes negligible. Similarly, for negative sequence also, that being balanced, the associated flux linkage to the other one also becomes negligible. That means that the positive and negative sequence component of currents, they have negligible mutual inductance, mutual impedance between these 2 lines. Come to the 0 sequence component. 0 sequence of, as we have already seen, 0 sequence component is I A 0, I B 0 and I C 0, they lie in the same phase, same direction. So, therefore, the associated flux of any line or any circuit, the corresponding contributed by the 0 sequence components, they become additive, and that results in that the flux becomes significant to link the other line conductors. So, therefore, the corresponding associated 0 sequence mutual impedance becomes significant as compared to positive sequence and negative sequence aspects. So, that cannot be neglected for different lines, and for example, for a 132 kV line, the data says that the 0 sequence component, as you have already seen, for the line individual line becomes 0.25 plus imaginary component 1 ohm reactance part per kilometer, where the Z 0 m, the mutual impedance per kilometer between these 2 lines, that becomes equals to 0.19 plus j 0.5 ohm per kilometer. So, you see here you can say that as compared to the 0 sequence component of the line, the mutual part is also significant. So, this says that from this that the 0 sequence current has a mutual impedance with the other circuit, whereas the other sequence component positive and negative, they do not have, they are negligible such impedances. So, this leads to our analysis for double circuit line little bit different than what we have derived for the apparent impedance calculation for single circuit analysis. Now, let us consider the double circuit line here. Phase A to ground fault we have analyzed, for other faults also similarly you can analyze fault in circuit 1, and we have a 0 sequence mutual impedance between this line Z 0 m. Note, this is a phase A to ground fault. So, therefore, V A at the fault point, that becomes equals to 0, but V A equals to V A 1 plus V A 2 plus V A naught. So, this is what the relations for such a situation. Now, voltage in phase A at bus M, the common bus for circuit 1 and circuit 2 relay bus. So, this becomes equals to V A 1 m plus V A 2 m plus V A naught m, but this individually we go to the sequence component the way we did in the earlier lectures on apparent impedance calculation. So, this V A 1 m equals to V A 1 f plus this drop. So, this is what this part, and we are only looking at circuit 1 now. So, therefore, V A 1 f plus I 1 m of circuit 1 and the corresponding impedance of that part here to here is x Z 1 m n, x Z 1 m n, where Z 1 m n is the impedance of this line, positive sequence impedance of the line, and x corresponds to the per unit fault point distance. Similarly, for the negative sequence component V A 2 f plus this part this drop. So, V A 2 F plus this drop. Now, you come to the 0 sequence component V A 0 F plus this drop, but now we can say that we have in 0 sequence we have a mutual component. So, therefore, for the circuit 2 the corresponding line has a mutual component of Z 0 m x Z 0 m, and then you can say that this x Z 0 m and the corresponding current associated is of the circuit in the second line. So, therefore, this corresponding relations becomes V A 0 F plus I 0 1 x Z 0 m n. So, this is the common like the earlier positive and negative part, but there is an additional component for the 0 sequence mutual part x Z 0 m into I A 0 m of the circuit 2. So, we are analyzing for the circuit 1 fault. So, relay at for R 1 for the circuit 1. So, for that the corresponding mutual part has the other circuit 0 sequence current. So, this is the expression for the voltage at for bus A for bus M at the relay location for the phase A to ground fault, and we are analyzing the fault at phase voltage relation. This you see your V A 1 F plus V A 2 F plus V A naught F, as we have seen, that becomes 0. So, this one, this and this, these 3 becomes 0. Now, we have all the other current components 1, 2, 3, 4 terms. So, now similar to the earlier single circuit aspect, if we take the x Z 1 m n and we know Z 1 m n and Z 2 m n, they become same. So, therefore, we can say that I 1 m plus I 2 m and I naught m similar to the earlier expression, this becomes that, and this is nothing but your our component of I A m component, phase A current component during fault. Now, if we go to the other components, if we see here, you can say that we have added and subtracted this part I naught m circuit 1 and I naught m circuit 1, this part like we did earlier case. So, this gives us I naught m x Z 1 m n Z 0 m n minus Z 1 m n divided by Z 1 m n, but there is another additional term for this component. So, this is what you can say that I naught Z 0 m x Z 1 m n Z 0 m divided by Z 1 m n. So, this Z 1 m n Z 1 m n that you can say that will cancel out. So, now we see here you can say that from this relation, so that x Z 1 m n I m, this part remains this, and we define you can say that k naught equals to the 0 sequence compensation factor Z 0 m minus Z 1 m n divided by Z 1 m n into I naught the first circuit current and the x Z 1 m n. Now, you can say that for this part if we see, we define you can say that I naught 2 m plus x Z 1 m n, same x Z 1 m n term we are putting, and we are putting you can say another factor k 0 m equals to Z 0 m upon Z 1 m n, where k 0 m is called the mutual compensation factor, and the reason behind that we have the 0 sequence mutual impedance between these two lines Z 0 m, and that is you can say that with respect to Z 1 m n, that factor is called mutual compensation factor. Note that to remember you that this k naught, the last say that lecture also discuss about 0 sequence compensation factor. In some of the literature we will find this you can say that take a factor of 3 in the denominator, and that is due to because the corresponding current that is being considered is the neutral current or the earth current. So, that becomes 3 times of the I naught. So, therefore, they remain same you can say in terms of that. Here we are considering I naught 0 sequence current, and that is why I can say that the 3 term is not here. So, from this one, from these relations we say that the corresponding x Z 1 m n is a common term in all the 3 terms. So, x Z 1 m n you can take it outside, and then this becomes equals to V m upon I m plus k naught I naught circuit 1 k naught m circuit 2 0 sequence current. So, in general we can conclude from this relation that this x Z 1 m n is nothing but the impedance up to the fault point, positive sequence impedance up to the fault point, that is what we say here. So, therefore, that we say you can say that in terms of the refer it as a Z apparent as calculated by the relay. So, Z apparent equals to V m upon I m of the first circuit, the circuit where the fault is there, the circuit where the relay is looking at, plus k naught the I naught the circuit 1 current 0 sequence current plus k naught the circuit 2 zero sequence current. So, this term becomes an additional term, and note that this requires zero sequence current of the circuit 2. So, for that the corresponding I A, I B, I C of circuit 2 are required to obtain the corresponding zero sequence current aspect. So, this derivation for the phase A to ground fault reveals us that for a double circuit line, the corresponding expression for Z apparent differs, and this difference you can say that is by this factor, the additional factor. Here you can say that this perspective. Now, note that this Z apparent now for this region becomes a modulated one as compared to this perspective. What the modulation is being done by this double circuit line is that the zero sequence current in the other line during that fault and this factor of k 0 m. So, this part with regard to this part may be additive or subtractive depending upon the corresponding phase relation of the I 0 m with respect to this part of the currents, these two currents. So, that means that you can say that the corresponding denominator becomes larger or smaller depending upon the phase position of this I 0 m in terms of these two currents. So, that leads to that if this value total value becomes smaller than this value, then the corresponding impedance will be larger, and impedance is larger means then the corresponding situation will be an under situation, and if this factor becomes additive and then this total impedance becomes larger as compared to this value, then the larger impedance means the corresponding value will be smaller, and that leads to an overreach issue. So, that you can say that the consideration you can say that if we consider only this part as usual which we have considered for the single circuit line. Now, I will go you can say that see this perspective of for the same circuit. So, if you consider the zero sequence current of the other line and considering the mutual aspect, we derive the equations as we see the in the last slide. Now, from this relation voltage relation and current relation, now suppose we do not take the corresponding current in the denominator, the expression the corresponding current this part to get the corresponding x z 1 m n, and if we take only that the single circuit line what we have seen earlier, if we take the expression of V a m upon I a plus k naught I naught, then what happens we see here. Then dividing with that this current, this relation becomes x z 1 m n, which is the fault distance actual one, plus there is another term x z 0 m m, z 0 m I naught 2 circuit 2, I naught circuit 1 plus k naught I am circuit 1 and k naught I naught circuit 1. So, this is additional term which we are getting for the double circuit line. If we use the same current relation and voltage relation for line to ground, phase to ground fault in phase A to ground fault as you have seen in the single circuit case. So, this additional term we can say that if this becomes additive, as I already said you can say that. So, that becomes overreach or underreach depending upon the phasor position of I naught in the I naught you can say that in the second line for the fault in first line. Now, let us go to an example. So, we have a double circuit line as shown radial systems, and we have Z 0 m f. The Z 0 m f corresponds to the zero sequence mutual impedance up to the fault point for this circuit with the circuit 2. This is a 230 kV system 150 kilometer, and we have line parameters Z 1, Z 0 and Z 0 n, the mutual zero sequence impedance, and the fault you can say that is being created at 100 kilometer. So, therefore, the corresponding Z 1 positive sequence impedance up to the fault point which the relay is expected to obtain from the Z apparent becomes 100 into this per kilometer impedance. So, that gives us 3.6 J 51.27 ohm. Now, we will calculate for this phase A to ground fault, a simulation was done for this circuit at 100 kilometer from this point, and we will observe the relay voltage and currents. So, this is the set of voltage phasors during fault, and this is set of currents I A, I B, I C for circuit 1, and this is the set of currents I A, I B, I C for circuit 2. In circuit 1, the phase A current is significant as compared to the other two phases. In circuit 2, the corresponding phase currents we see here, there is no significant change like in case of circuit 1 for this case. Now, we see here we require not only these first circuit currents, we require second circuit currents to calculate the zero sequence current of the second line. So, the task is to calculate the apparent impedance seen by the relay at M. Now, two approaches we will see, as already discussed earlier, that only using the circuit 1 current and voltage and also using the circuit 2 currents also, agree. So, the simple relations of V A divided by I A plus K naught N naught, and the other one you can say that V A upon I A plus K naught N naught plus the K 0 I 0 2, the circuit 2 perspective K 0 M I 0 2. So, for these solutions we will find the corresponding zero sequence current for circuit 1 from this relation I A I B plus I C upon 3, and we got the corresponding this for the circuit 2 also we got like this. Note that the zero sequence current here they are close to each other, then the corresponding they are almost in phase kind of thing, that results in you can say that an additive factor in the denominator as we have discussed earlier. The K naught equals to Z 0 M n minus Z 1 M n upon Z 1 M n. Already in the single circuit we have analyzed this. This becomes equals to, if we divide by the kilometer distance length of the line 150 kilometer, then it got the small z 0 minus small z 1 upon small z 1. This small perspective is nothing but in terms of the per kilometer basis, these values which are provided here. So, K naught you can say that is a complex number obtained. Now, K naught m for the mutual perspective, it z 0 m upon z 1 m n. So, that can be also small z 0 m upon small z 0 m divided by the length of the line. So, that comes out to a complex number. So, these two factors are having a complex terms. Now, we will apply the two approaches without considering mutual coupling, means without considering the second line currents. So, this simple considering a single circuit approach V A upon I A plus K naught I naught. So, this becomes equals to substituting the values, we got this to be 6.95 plus J 52.93 ohm. So, this says that this value is higher than this actual fault positive sequence fault impedance up to the fault point from the relay, that is what our comparison 3.6 J 51.27. So, this should be a higher value. So, that means that if you use this formula like the single circuit approach, then this relay will underreach, this relay will underreach. Now, if we consider the mutual coupling of the between these two and use the second circuit currents to obtain the zero sequence current for that circuit and use the formula like which you have derived. So, then V m upon this, then this becomes 3.6 J 51.27, which happens to be exactly equal to the Z 1 M F, the positive sequence impedance up to the fault point from the relay location. So, that means that the relations which you have derived is in agreement with the corresponding positive sequence impedance actual one, and if you use these relations using the currents from the second line, then we will be getting more accurate apparent impedance. So, there will be no issue of underreach or overreach, whereas if we neglect that part, then there will be, in this case we observe that this will underreach. But again, if the corresponding this current becomes its phasor position with respect to this becomes deviate significantly, then we may find you can say that this also, the other way you can say that the overreach phenomenon also, overreach issue also. So, with this we see that you can say that zero sequence mutual coupling is of significance to distance relay apparent impedance calculation also. Now, we will see you can say that what are the different challenges associated with the circuit operation. One is that a double circuit line, what we have seen in the earlier diagrams, that at times if line may be out of service due to maintenance and so. So, generally what is being done, that the line at the both ends they are being grounded, but with that grounding what happens, that the corresponding, if a fault happens to be in the circuit 1, if a fault happens to be in the circuit 1 and circuit 2 is grounded, non operational, then these points will look like this through ground. So, therefore, there will be zero sequence induced voltage in this circuit, and that zero sequence induced voltage will circulate current in this one, and that current will be in the opposite direction, that what we have seen in the earlier case. So, in that case it is being said that the relay has a tendency to overreach. So, therefore, care should be taken for the zone 1 setting for this kind of situations. To overcome this, many recommend for, you can say that not 80% of zone 1, 65% of zone 1, 65% of the positive sequence impedance for zone 1 for such condition only. So, in case of only single circuit is operational for a double circuit line because of this mutual effect. However, such a fault for single circuit operation during the other line not be analogized is very rare. So, many utilities they do not go for, you can say that this lower setting of positive sequence, lower setting of the zone 1, they continue with the, consider the highest normal setting of 0.8 to 0.9, you can say that of the Z1Mn. Another challenge is the cross country fault. So, what I mean here, that suppose line 1 has, you can say that a phase A to ground fault and associated with this arcing, and so a fault may be triggered in the other line or circuit in another phase, like here in this case we have shown phase B to ground. So, what will happen, that both, you can say that distantly at this point and this point, or from the other side also in the network, that they will see significant current in phase A and phase B. What I mean to say is that a fault is there in AG, and therefore, you can say that phase A current will be significant. Now, a fault again following that it triggered in phase B of the other circuit. So, therefore, from this you can say that a path, you can say that from the phase B part you can say that goes to this. So, in phase B current also at this you can say that relay position also will become significant. So, that results in that the corresponding relay at this point, distantly at this point, will see the fault as not at AG fault, will see the fault as ABG fault. Now, if the relay sees this as ABG fault, then it will use the corresponding relay of, we can say that VA minus VB divided by IA minus IB, not VA upon IA plus IA plus K naught I naught plus the K naught M I naught 2, agree. So, that means what I say that this is a situation of cross country plot, and such a fault produce fault current contribution is in both the circuits for phase and this. A multi-phase consider fault causes phase tripping. What I mean to say that if this corresponding relay sees the corresponding fault to be the phase ABG fault, then the auto reclosing business it will be considered as a 3 phase tripping aspect, whereas only a single phase to ground fault happens to be there. If single phase can be removed, and here also single phase can be removed in phase B, then also you can say that the system can run, and then you can say that again you can revoke the systems after some time. So, this is what you can say that about parallel line brings issues, you can say that to distance relay based protection scheme. Now, we discuss on the issues on compensation factor, the zero sequence compensation factor contributed by the other line, other circuit. So, we discuss mostly on zone 1, but in many aspects for zone 2 you can say that the corresponding impedance setting is not being taken care in general, because zone 2 setting we have extended either from 120% to 150% of the corresponding line being protected. So, that factor of larger value of we can say that zone 2 to take care the whole line of zone 1 gives having sufficient safety margin. So, therefore, we can say that on this perspective we can say that the zone 2 may not be in trouble. Zone 3 however, is a backup protection for the subsequent line from the remote bus. So, therefore, there must be a check whether this mutual factor is of significance in terms of that, and that may be a that zone 3 setting should be of concern, and so therefore, the mutual aspect must be considered for the double circuit line. Note that as already mentioned at the earlier, the lines may be partially coupled. It means that they may be a common portion on the right of way for the part of the line, then that becomes you can say that more introduces more complexity in the system, because of depending upon the fault position and so. Current information of the second line may not be available, because they may not be having common bus at the relay side. So, if the corresponding two buses are of distance apart, then we cannot get the corresponding currents from the second line. In distance protection, the compensation for the mutual compensation is applied in case like where sufficient reach of the backup zones would otherwise not be possible, like if you say a short line followed by a long double circuit line. So, short line we know the issue, you can say that how that is for the its backup protection. Zone 2 of the first line, maybe double circuit line, longer line may go beyond, you can say that the zone 2 of the subsequent short line. So, that may be issue. So, that is why I can say that it may be critical in that perspective, and if that is important from that perspective as a backup protection, then this may be followed. Otherwise, the using the relation for the apparent impedance calculation using the compensation factor, zero sequence compensation factor, considering the other line currents is not widely being used in the industry, because of this complexity of so many issues, configuration issues, and single circuit operation and so and so. However, for other applications like the fault location and so, the zero sequence current of the other circuit becomes useful to correct for the proper impedance calculation and so. So, in that case that can be successfully used. So, this is on we learn on how for the double circuit line the distance relay can be applied and the associated issues and the corresponding practice in the industry. Thank you.